My name is Nabawanga Afwa, and I'm going to go through part number 1 of our practical assignment of data structures and algorithms. So, part number 1 basically it involves the TSP representation and data structures. When I talk about TSP, I'm basically talking about the traveling salesman problem. Yeah, so we're going to see how we go ahead and represent it plus the data structures. So basically, it's graph representation. Like we are given 7 cities, those are the nodes with edges representing distances between the cities. Then we used the graph adjacency matrix to represent and store the distances. So before I continue, first of all, when I talk about the adjacency matrix, it's basically a square 2D array, just like you can see, like the justification for using this graph adjacency matrix. So it's basically a 2D array or matrix whereby rows and columns represent cities or nodes, and cell values go ahead to represent the distance between the cities. So we have positions, that's I and J. So basically these positions in the matrix indicate the weight of the edge between like vertex I and vertex J. And if there is no edge between the two vertices, then the value is typically set to infinity or any other number, maybe I don't know, 100, 1,000, or what, up to infinity, or maybe 0, like depending on the context. So basically we this presentation, like we just gonna explore how to represent this traveling salesman problem using a graph. Yeah, so okay, in the very first place, this traveling salesman problem like basically involves finding the shortest route that goes to visit like each city exactly once without returning to the same origin. So basically, let's go through this graph representation. So this adjacency list representation, just like I talked about recently, we have rows and columns basically to represent cities, then the cell values represent the distance between the cities. So we can see basically from 1 up to 7, these are our cities. Then the distances, we can see that city 1 connects to city 2, then 3 and 7, like 3 and 7, that's the distances are 10 and 12 respectively. Then when we go to city 2, we can go ahead and see like it connects to city 1, and 3 and 4 for 8 and 12, yeah, respectively. Then the same ish, like we go ahead and do the same thing for maybe, okay, let me take another example. That's for this is city 6. We go ahead and see that city 6 connects to city 4, and then connects to city 4. Then 5 and 7 by there is like this is city 4, like this is city 6, it's connected to city 4, 5 and 6, and these are the respective distances. That's 10, 6 and 9. The same ish here, that this is city 7, go ahead and connects to city 1, city 3 and city 7. Yeah, city 7, go ahead and connects to city 1, city 3, city 5 and city 6 with respective distances. That's 12, 9, 7 and 9 respectively. So one might question themselves and be like, why did we go ahead and decide to use adjacency matrix? So basically the reason is our first reason is efficiency, whereby the graph for this TSP problem contains only edges between directly connected cities. Yeah, hence faster lookups for neighbors. Then with the adjacency lists, went ahead to see that cities connected to a specific node can be quickly identified, which streamlines the process. Yeah, like it's basically clear. So we went ahead and see, for simplicity, like the structure is straightforward and easy to implement. That's why we use an adjacency list presentation. So making it a good choice for educational purposes and for small to medium-sized graphs. So basically, someone can, okay, why should someone decide to use an adjacency list? It's basically because, okay, if you have like small or medium-sized graphs, you can go ahead and use it. Like for example, in this situation, we had just 7 cities, so basically it was okay. Then for space complexity, the space complexity of an adjacency matrix is basically this, where V is the number of vertices, and yeah, this can be efficient for sparse graphs. That's our graphs with relatively few edges compared to the number of vertices. So, but for dense graphs, those are the graphs with a number of edges close to V squared too. Then for the problem setup, the objective was basically to visit each seat exactly once, just like I talked about it previously, that our main, like basically the like once without even returning to the origin, something like that. So our main objective was visiting each city exactly once and return to the starting city while minimizing the travel distance. So our assumptions, basically the graph is fully connected. Yeah, the graph is fully connected, and also the distances are symmetric. What I mean by symmetric, it's basically like the same cost in both distances. Yeah, that was my presentation.
My name is Osabarike John, and I'm going to be taking you through our number one. So yeah, I'm going to be taking you through number one. So I am going to walk you through how we represented the traveling cells problem using a graph data structure, and I'll briefly discuss the choice we made. First, let us understand the problem itself. So the main objective of the TCP is straightforward: visit each city exactly once and return to the starting city while minimizing the traveling distance. So now to represent this problem, we chose to use an adjacency matrix, which is a common and efficient data structure for graph representation. So in this matrix, the cities are represented as rows and columns. So the value in cell I and j corresponds to the distance between city I and city j. So if there is no direct path between the two cities, the value is going to be 0, as you can see here in our code. So the reason why we chose this data structure is that it allows constant time lookup of the distance between any two cities. So in this matrix, if I want to know the distance between, let's say, city 1 and city 2, I'm going to access it using their index, which is 0 and 1, and this is going to give me a 10, and that's going to be the distance between those two cities. So next year we went ahead and we created a graph object, and this we used a NetworkX, a Python library that simplifies the creation and the manipulation of graphs. So, and here it's how we happen to add the edges to the graph, and these edges are going to be added if the distance between those two cities is greater than 0, and that's going to show that there is a connection between those two cities. So finally, we used the matplotlib and the NetworkX to visualize the graphs, which allows us to better understand the connection and the visual, which allows us to better understand the connection between the cities. And the moment you happen to run this code, you are going to get this visualization. So this visualization shows cities as nodes, and the distance between the cities as edges, and Yes, and I think
My name is Paul. So my colleague talked about the graphical representation of the problem. Me, I will talk about the solution to the problem. So with the solution to the problem, we decided to use the nearest neighbor algorithm. And in this algorithm, our main target was to achieve the optimal path and the optimal cost. So in this algorithm, with this algorithm, we started with the pseudocode, and then after we wrote the Python code. So in our pseudocode, we define the function as nearest neighbor, and then we initialize the array to track visited cities. We initialize the array to store the path starting from the given city, as in the start city, and then we initialize the total cost to 0. So still with this pseudocode, we have a main loop. With this main loop, it loops through it loops through all the cities except that city where we start from. And then inside the main loop, we have another loop that that loops through the nearest unvisited city. And in case a city is not visited and its distance is shorter than that we have just visited, we update the the city as we update the path to include that nearest city. And then we also update the minimum distance to that distance of the last city that we have just visited. And then in this pseudocode, we return the optimal path, as I told you earlier, and the optimal cost. So with our code here, as I told you, this is as I've just told you, this is our adjacent matrix representing the distance between the cities, as my colleague talked about it. And then this is our function. This function implements neighbor algorithm for solving the traveling salesman problem, as I told you. And then this is our main loop, and this is the other loop inside the main loop. So on running this code, you return the optimal route as the optimal path and the optimal cost. So on running this code, obtain the optimal route or the optimal path as 0. From 0 we go to 4, from 4 we go to 5, from 5 we go to 6, then 1 to 2 to 3, and then we go back to 0. So for that case, our minimum cost, as in the optimal cost, is was obtained as 57. So that is what we add for you, as in that is what we try, as in that is what we tried to. So that was the solution to our problem. So we were able to find the optimal path at 0, 4 to 5 to 6 to 1 to 2 to 3, then back to 0, and the optimal cost at 57. So what's it?
that's all that I have for you. Yes, thank you very much.
Hello everyone, my name is and I'll be taking you through the presentation where we worked on solving the classical traveling salesman problem. So, in this presentation, we'll take you through the algorithm choice. I'll take you through the implementation and the results. So, however, let me first share the screen. So basically, this is what I'm going to take you through. So first is the brute force approach, whereby the brute force approach involves generating all possible permutations of the cities and calculating the total distance of each permutation. So for the brute force approach, we calculate all the permutations for everything. And after calculating all the total distances, we find the shortest distance, and that's the solution. So for brute choice, we see that the general solution is optimal since it calculates for everything. So the time complexity for brute choice is O(n) factorial, where n is the number of cities of all the cities. So moving forward, we have the dynamic programming approach. So this approach is more efficient than brute force and uses the memorization to store intermediate results. We see that the dynamic programming approach basically uses it memorizes the results and then stores those intermediate results. So we see that it is more efficient, so it reduces the time complexity to big O notation n squared times 2n squared, 2 power n. So its time complexity is this, which is significantly better than the big O notation n factorial for n larger. Moving forward, we have the approximation algorithm, which is the nearest neighbor algorithm. So basically, for instance, of the TSP, the exact solution becomes impractical. Like we see that this solution is not optimal. Like it's not the best solution to choose, but it's the simplest and the quickest. So in our presentation, we had to choose the nearest neighbor algorithm. So what we are doing basically is we're having many cities and different distances. They covered different distances between them. So our goal here is to, using the nearest neighbor algorithm, our goal is to go through all the cities exactly once without repeating them, and then finding the best and the best distance, which is the nearest distance. So going forward, we use the Python code to implement our algorithm, whereby we visited this code here helps us to track the visited cities. Then we have to start from the first city, and then we go on marking the visited cities. So here we use the for loop for all the visited cities. Then we had to get the last visited city, then the nearest city. We also used here a for loop again for the nearest and visited cities. Then after we have all visited the cities, we go back and we go back to the starting point where we started from. So basically, our algorithm works like we start at an arbitrary control city, whereby we start at a certain city. We mark the current city as visited. Then we find the nearest unvisited city and move to that city. Then we also mark it as visited. Then we repeat the process until all the cities have been visited. After that, we return to the starting city to complete the tour. So when we are done with visiting all the cities, and we are done with, we have returned to the starting city, then the tour is done complete. So what we do after this, we see the shortest distance, and that is the one that we use. So basically for our presentation, we chose to use 4 cities, and we saw the shortest distance, and it was from city 1, city 3, then city 2 back to city 1, and it covered a distance of 80 kilometers, and which was the shortest distance that we had covered. So basically, when we use the nearest algorithm, the nearest neighbor algorithm, it's quick. It's simple, it's quick, it's fast. Like for small data, it's the best. That's why we chose it. Thank you.
Hello, this is Dastan, and I'm going to take us through the self-organizing map approach to solve the traveling salesman problem. So the first things first is to take us through the conceptual overview, and that in the conceptual overview we also have an explanation showing the challenges. All right, so basically a self-organizing map is an unsupervised neural network. It organizes the dimensional data into a low dimensional topography while preserving spatial relationships. So for this case of the traveling salesman problem, the SOM is adapted to arrange the neurons, which are the specific cities taken in as the input, and it represents them as a cyclic tour. It iteratively adjusts the neuron positions to approximate the shortest route all cities are only traveled to once. Alright. Self-organizing map architecture and the process and the training process. So first of all, the cities are taken in as neurons in the input, and we have 7 cities, so that means you have 7 neurons, and they would be arranged in a circular topography. So the cities are like input vectors in the 2-dimensional coordinates, and then during training the SOM adjusts neuron positions to align these city locations. The ring structure ensures that the route is close. This mimics the traveling salesman requirements to return in the starting city. So that's just the representation. The training steps. So in training steps, we have neurons that are randomly placed in a 2D space. We have other parameters like the learning rate, neighborhood radius, and a number of epochs that are set. Now the winner selection is for each city. The neuron closest to it is selected as the winner. So city 1, there are like 2 cities, 2 and 3. As we get the win, so when we find that city 3 is closer to 1 and city 2 is closer to 1, we go with city 3 as the winner. But then that keeps on updating the neuron. So the winning neuron and its neighboring neurons are moved closer to the city. So there's a function which is called the Gaussian neighborhood function that determines the extent of influence on a nearby neuron. So does this affect the other nearby neurons? So if you are extending city 3 to city 1, then you impact neighboring neurons to city 3. So you have to keep updating that. So that the learning rate and the neighborhood size decrease over time for gradual convergence. So the process be able to get the winning the winner. So that you adjust neurons, you have to iterate through all the cities, and so you repeat it until you have an optimal city position. In that whole state of finding the winner and then adjusting the neurons, you have to now extract the route and the result. So the order of the neurons determines the sequence of the cities to be visited. The final route is extracted by mapping neurons to their closest cities, and the total distance is computed by summing up the Euclidean distances between the consecutive cities. And then the SOM solution provides a practical balance between the accuracy and the efficiency. Now, in our assignment, we are required to also give the challenges. Some of the challenges are all limitations or difficulties that we have to face when you are using this SOM approach to solving a source person problem. All right. So there are advantages in it. So the SOM is scalable, so more than the classical approach. It can handle noise, so in case you have missing data, so the weights, let's say the distance between certain cities are not being inputted, at least it's able to adapt to that. And finally, the visualization. So because of the Turing structure that is visualized using this approach, you're able to present the solution very well. Challenges: parameter sensitivity. So because you have to select the learning rate and your neighborhood function, so your logic in the neighborhood function will affect the performance of the algorithm. Local minima. The algorithm may not always converge to the optimal route. And then symmetric issues. So asymmetric city layouts whereby directional paths have different costs. So it may struggle when you have different costs between the bidirectional path to the cities. Yeah. And then a conclusion: the self-organizing map provides an effective heuristic approach to solving the traveling cells person problem by mapping city locations onto neural network and iteratively refining the neuron order. While it does not guarantee an optimal solution, its balance between computational efficiency and accuracy makes it a useful alternative for the moderate traveling salesperson instances. Right, this is just a conceptual overview of how the self-organizing map operates. Now, on our next thing, we are required to just provide step-by-step pseudocode, really step-by-step pseudocode, and then also give the results. Okay. So number 3 here we have the pseudocode. So pseudocode is something really short. We have the key functions here. Is this one uses for removing duplicates to ensure that we have a valid route. This one is for finding the closest city, and then this one is for calculating the Euclidean distance, because we want to get total distance that is what we traveled by the source person. So first things first, you are going to initialize the training, the learning rate, the neighborhood radius, number of neurons, same as number of cities. In this case, you do all that when you're beginning the code. So they are just the hyperparameters, you have initialized them, and then next one is now you place the neurons in randomly the 2D circular path. Just place them randomly, and then here the training begins. So you look through the cities, and while you look through them, you have shuffles. You go through each city as going through it to look for the nearest city, look at radius, and then you determine. So if I'm at city 1 and look through to go to city 3 and then city 2, how close is which one is closer? So if city 3 is closer to 1, then city 2 is closer to 1, so you move city 3 closer to 1, and you also check the influence to ensure that you are not affecting city 2. You find the winning neurons once you have found it, which is, for example, city 3 is now closer to city 1. You update also the neighbors. So if city 3 is being moved to city 1, does it influence maybe city 5 the other side? So it also moves closer, so you're moving them towards the city. So iterate through them. So once you're done iterating through the cities, then now you find your final result, final route to be used. Yes, final route to be used. Yes, so you based on the position where you are, you get the nearest, and then just keep appending them to the result route, the final route. This is just to remove the duplicate routes so that we have a valid tour. Then you compute the distance, because you want the distance that's going to be traveled by the salesperson, and then you give in the final output of the result. Alright, then this is all the code. So the result for it, you go to route here, final result is this. So these are the step-by-steps to getting the distance. So you go for 1 to 3 units, 3 to 5 data, this to this to this to this, then you get the total distance that's being traveled by the traveling salesperson, and also the route that is going to use. Yeah, and so that kinda goes into answer our assignment here. So how the approach uses the self-organizing map for the approach. So this again, this is Dastan who has been explaining the number 3 of how to use self-organizing map approach to solve the traveling salesperson problem. Yes.
Yes. Good evening, everyone. Yes. This is Charisma Carlos, and I'm going to take you through number 4. Okay. Yes. Let me just disable my video for a minute. Yes. So I'm going to take you through the analysis and comparison of the classical solution, of which for the classical solution we use the nearest neighbor, which is a greedy approach. Then the other one was the self-organizing map approach. Yes, like my colleagues have taken through earlier, the classical traveling salesman problem, we use the nearest neighbor, which for the nearest neighbor, this one looks at the 7-city graph that we had, then compares from the start state we had, then from there it goes on to traverse the next unvisited state, the closest unvisited state from the start state. Then from there traverses all other cities while saving the next the unvisited state. So after traversing all the states, completes, then returns to the start state, then completes. So for the nearest neighbor, it's guaranteed to give you the nearest the fastest route. So that's why for the comparison, using we first looked at the distance, the nearest neighbor was the shortest route, as it traversed all states and gave us a total distance of 57 that was covered. Then for the self-organizing map, this is an unsupervised learning technique where it looks at the map that has been given to us. That was the 7-city graph. It looks at the map that has been given to us. Then from that map, it uses each state on the map as a neuron and the distance to the next state as the weights. So how it traverses through, how it like maps, this one organizes through unsupervised learning, it looks at all the states, organizes them into a 2D map. From a 2D map, here, it looks at the initial state, the one you consider the start state. From the start state, it looks at the characteristics of all other neurons. Then from all the other neurons, it marks the winning neuron. So for the winning neuron, this one could be having the characteristics that could be where it should be traveled next. So it continues all like that till all the neurons have been arranged on the 2D map. So using the self-organizing map, it gave us a total distance of 69. So in this case, the classical TSP solution using the nearest neighbor was the shortest route, like the table shows. So the complexity of the nearest neighbor has the time complexity of the nearest neighbor is n squared. Like you can see from here, it is n squared, where the n is the number of cities. Yes. Then the space complexity is just simply this is it, the ON. So this is the space complexity, and then this is the time complexity. So for the nearest neighbor, this one is not optimal, but it guarantees to give you it guarantees to give you a route, but is not optimal, as it leads to many local maximas. Yes. Then we move on to the self-organizing map. So for the self-organizing map, has a time complexity, which is for each city, captures the distance of all neurons, like I've said. Therefore, the overall time complexity of the self-organizing map will be the T, which is the number of iterations, and the N, which are the neurons, the N squared. So the time complexity of the self-organizing map from this, the other one was N squared. It is arbitrarily higher, like you can see from here, but they have the same space complexity of N. Since this one, N represents, for each city, we marked each city as a neuron. That's why I'm using capital N here, not the city itself. So each city is stored as a neuron. Yeah. So they have the same time, but the time complexity of the self-organizing map is higher. So we moved on to the practical considerations, whereby we noted that the nearest neighbor algorithm is better for the smaller number of cities. Yes, where the number of cities is smaller, the nearest neighbor is better. So then, so for the reason which said for when a high accuracy is required in scenarios where the cost is suboptimal, the route is significant, then an exact solution is preferable. An inexact solution, we consider the nearest neighbor. Then for the heuristic solutions to solve the problems of the self-organizing map, we came up with using the hybrid methods. But for the self-organizing map, it's better for a larger data set, since I've said for we feed the map with data with no labels. So this one is an unsupervised learning model. So we just feed it with data and it learns on its own and organizes the data the way, like in an easier way. So for the larger number of cities or a larger data set, a heuristic method like the self-organizing map or genetic algorithms are more practical due to the lower computational cost, since you don't have to store everything like for the nearest neighbor, where you have to store the unvisited cities. Yes. Then for the time constraint, in real-time applications where a quick solution is needed, then a self-organizing map will be better. In planning, like real-time routing planning, these provide a good trade-off between the speed and accuracy. Then also, when the resources are limited, memory is a concern. Since you don't store everything, it learns on its own and we just store the characteristics. So memory usage is a concern. When memory usage is a concern, then heuristic approaches like the self-organizing map can be more efficient, as they do not require storing all the possible routes. So for the nearest neighbor, you have to look at all the nearest the states nearing the initial state. So after that, you store those states, look at those states, which one could be near, which one could be recognized as the nearest state, then take that state. Then again, you save the next unvisited states so that can be, then they're stored next. Yes. So also, for the extensions I've told you, like we combine the self-organizing map with the local search algorithms. This solution obtained from the solution, this can be, combine the self-organizing map with the local search algorithms to refine the solution obtained so we get the solution obtained from the self-organizing map, then we add it with we combine it with the local search algorithms. So for the local search, we are talking about the depth first or the breadth. Yes. Then also we can consider advanced heuristics, implementing advanced like the anti-colony optimization or genetic algorithms that are specifically designed for the TSP. So these are the solutions we came up with an optimal solution for the problem. Thank you so much.